Good morning, everyone, and thank you for joining us today. My name is Rosie, and I'm the Communication Manager for the NACOE program. Today, I'm pleased to introduce the A67 webinar, Network Lifecycle Model for Embodied Carbon and Emissions. Next slide, please, Daniel. Firstly, I would like to acknowledge the traditional custodians of the land we meet and pay my respects to the elders, past and present. I extend that respect to Aboriginal and Torres Strait Island people here today. Next one, please, Daniel. So NACOE, or the National Asset Centre of Excellence, is a collaborative research initiative between the Queensland Department of Transport and Main Roads and the National Transport Research Organisation. The partnership is focused on delivering engineering excellence through leading road asset research that welcomes innovation and drives road management practice efficiency. Next slide, please, Daniel. Thank you. So by way of housekeeping, today's session will be recorded and it will be made available on the NACOE website and YouTube channel. There is a Q&A feature which you'll find at the bottom of your screens, so feel free to add questions throughout the webinar, which we'll answer at the end of the session. Lastly, there will be contact details at the very end of the webinar if you'd like to get in touch with the team. Thanks, Daniel. Today's webinar will present findings from NACOE research, examining the greenhouse gas emissions and economic impacts associated with pavement maintenance and vehicle electrification. To present these findings, I'm joined by today's presenters, Dr. Daniel Annalise and Rohit Kurian from NTRO, Andrew Golding and Michelle Barron from TMR. I'll now hand it over to Daniel.
Thanks, Rosie. Good morning, everybody. So today we'll run through the main sort of methodology and results and findings of this NACOE project that was completed. So just to do a quick acknowledgement of the project teams that were involved. So from our side, there was obviously myself and Rohit who are here today. We've also got Dr. Robert Cohan and Tyrone Toole as well, who's on the call. And then from TMR, it was Andrew Golding, Abraham Green, and Michelle Barron. So this project has a number of linkages to previous NACOE projects. They're listed here. There's a few different ones across some of the different streams of research that we work in. And so I think if there's any questions, you can find these on the NACOE website, some of these reports, and then there's a couple more that are coming out shortly. And so I'll start with a bit of an overview of the project and the research that we undertook. And I'd like to hand over to Andrew to talk to the project objectives from a TMR perspective.
Thanks, Daniel. With the push to net zero greenhouse gas emissions, TMR and broader government need to understand the implications of our maintenance, preservation and renewal treatments in terms of not just the embodied carbon from those treatments, so the carbon cost associated with our work activities, but also the resultant enabled carbon emissions for road users. From an asset management perspective, that's important because we need to consider in our life cycle analysis how our investment choices affect our road users. So that doesn't just apply to their direct costs associated with fuel and wear and tear, but also relating to their emissions. So this project sought to address the gap in our knowledge on carbon emissions associated with our maintenance and major pavement renewal activities, and to inform the emissions estimated under multi-year life cycle network analysis undertaken while we're developing our maintenance and preservation programs. We had two key objectives in mind. So firstly, to extend the coverage of the SAT4P maintenance libraries and processes to help inform our rehabilitation treatment selection. But secondly, then to provide estimates through lifecycle analysis of the carbon impacts of our major components of the maintenance, preservation and environment investment program, including those the impact of the impact from the level of deferred maintenance. So it's important to consider the associated emissions cost associated with our deferred maintenance. I'll now hand back to Daniel. Thank you.
Thanks, Andrew. So I thought I would just start with a bit of context in terms of, when we consider terminology and there's lots of different carbon terms. If we like to think of things, if we think of it from an asset perspective or, an infrastructure perspective, it's important to consider that whole of life carbon. And so what that you can break that down into is the different phases of, the asset's life. So if you look to the left of this diagram, there's the upfront carbon. So this is the, carbon or greenhouse gas emissions. I'll use those terms interchangeably throughout this webinar today. The upfront carbon looks at, what are the carbon emissions associated with the input materials, the transport to the construction site and the construction of those of that infrastructure. So it's sort of once you get it ready to be used, and that's really what is the focus of a lot of initial pieces of work. It's how much carbon is associated with putting together some infrastructure. If you then move on, there's sort of the infrastructure or the asset gets used, it has its operational life, and there's emissions associated with that around things like maintenance, repair, replacement, refurbishment. There's all those sorts of things that you'll be doing, those activities to keep the asset in good condition or keep it going. There's also then down the bottom there's operational carbon. So there would be things like operational energy, water, and other processes. So operational energy, if we think of it from a transport infrastructure perspective, is most likely associated with things like lighting, or if you've got a tunnel, there's some ventilation or HVAC. Then there's the user carbon down the bottom. So that's your road users who would be using your asset, and the emissions associated with the vehicles traveling on there. There's also, the end of life. So what do you do at the end of the asset's life? There's emissions associated with its, deconstruction, demolition, disposal. And then if you're looking into circular economy pieces, then you need to think of, well, are we just disposing of all these materials, or are we trying to recover them and then reuse them or recycle them into different applications going forward? So that's just a quick sort of overview of the whole of life carbon. We did some previous research a few years ago when we were looking at pavements, and we were looking at the impacts of, each of these different elements into, what's their contribution to that whole of life carbon. And so some of the sort of headline findings from that was there was 95% of the whole of life carbon was associated due to the enabled emissions, that B8 category. And this is essentially the users who are, using the road. So the vehicles driving over that asset, around 95% of the whole of life carbon is associated with that. Another finding was pavement surface condition. So the roughness primarily can contribute anywhere from 1 to 3% of the enabled emissions. And that's through obviously increased roughness of the surface, and then there's also some increased rolling resistance effects. And another interesting finding was that, the maintenance carbon emissions. So when you're, over the life of the pavement, you're, performing various maintenance activities, that those carbon emissions are often greater than that initial construction phase carbon. And so if we take those findings of, maintenance has a significant impact, and the enabled emissions are, by far the greatest component of that whole of life carbon. There's another factor that's being, introduced now, where we're seeing, low and zero emission vehicles. They're increasingly being adopted. So we're seeing that, you know, not just in the sort of passenger and light vehicle space, but we're now increasingly seeing them in the heavy vehicle space. So we're seeing a number of, electric heavy vehicles are starting to come out onto the roads, and they're replacing our, conventional, internal combustion engine vehicles of, diesel and petrol. And so, low and zero emission vehicles have a number of challenges. They are, we're changing the fuel source. So if you think of a switch from, say, a diesel truck to a battery electric truck, you're moving from a diesel tank to batteries on board. And so these vehicles are posing different challenges in terms of, can you maintain the same freight task? And there's also a lot of challenges around increased axle loads from that change in fuel storage on the vehicle, or energy storage now on the vehicle. And so the impact of these, new vehicles on the road network also need to be understood and accounted for, because they'll have an impact not just in the carbon footprint, but also in, managing and maintaining that network under increased loading conditions. And so this project also supported and fed into one of our parallel NACOE projects, which was called A68, Impact Assessment of the Introduction of Low Emission Heavy Vehicles on Road Transport Infrastructure. And so just a brief overview. So this project A67 ran for 2 years. In the first year, we focused on really it was a review to, establish what's the best practice for modeling enabled carbon emissions, and also reviewing pavement treatments under the MPE program and development of a wider catalogue of embodied carbon emission estimates. And then throughout the second year, we worked on developing a series of demonstration tools. And so we'll talk a little bit about that soon, but that was one to calculate the enabled emissions, and also to calculate the embodied carbon from maintenance treatments. And then we also then applied those tools to a trial application of a framework, and that was really looking at, can we generate some results and get some further insights into what is the, what are the changes in in carbon from, from enabled emissions from the vehicles, and also the impacts of the maintenance emissions as well. So now let's go to emissions modeling. So I'll start with the enabled emissions modeling focus. So when we started this, we were looking at what data currently exists within TMR, so particularly within the pavement management system, that can be, be made available to estimate carbon emissions. So what sort of data do we have that we can start with? So the main data sets that we identified were the average annual daily traffic, so AADT, and that composition. So what's the breakdown of that daily traffic? Is it, passenger vehicles? Is it heavy vehicles? What sort of classes they are? There's information around road geometry, vehicle travel speeds along those different, along the different roads, and also pavement condition, primarily roughness. So from starting with this data, we then look to develop a framework to incorporate this data where we can estimate the carbon emissions over an individual road segment, and then how can we use that to then scale it up to a network level. So in terms of the, modeling, we've spent a number of years working and really putting together a lot of the pieces for the ATAP guidance. So we have been looking, a suitable method that can be applied using the data available is under ATAP PV2 road transport. And what this model enables us to estimate for the different types of vehicles, fuel consumption. And we've also done some adjustments for electric vehicles to be able to calculate the energy consumption as well. But the basic approach for the fuel consumption is there's a number of different empirical factors, and we can scale them depending on various inputs. So if we look at this equation here, a number of the inputs we can see are there's the vehicle speed, so how fast is the vehicle going? What is the roughness in terms of the International Roughness Index, the IRI? What is the gross vehicle mass as well? So the vehicle mass will also have an impact. And then K1 to K5 are model coefficients, and they depend on things like road geometry, elevation and other factors. So we can get estimates for fuel consumption or energy consumption, and then we can take that fuel consumption in a litres per kilometre unit, and we can combine it with a carbon emission factor, so an emissions intensity, and combine that with knowledge of that sort of road section or segment in terms of its length and total traffic, and that can give us an estimate at an individual road section level. What are the emissions there? So I've got a bit more detail just of that sort of process. There was obviously some work that we had to do around vehicle matching. There's some, what the vehicle types that you have, for instance, typically in pavement management systems around AEDT, how can you sort of convert that to a vehicle or map that to a vehicle that is, aligned with the modeling framework? So we've done a number of bits around that. We've also, pulled data from various sources around looking at, distributions of vehicle types, distributions of vehicle types across the different classes. We've pulled out some data from the National Greenhouse Accounts factors around emission factors, and then really just combining that to work out at that road segment level, here is the total emissions across that section. And so as part of this, we've also developed these demonstration tools that I mentioned earlier. So under that framework, we've got two spreadsheets that we've developed. So this first one is around how you can use it to calculate the greenhouse gas emissions from the enabled emissions. What I've just got here is just a little screenshot of the main sheet, which just outlines all the different individual sheets that form the demonstration tool. So it's a standalone tool where you can, see how this framework has been implemented to calculate the user emissions. So it's got a workflow sheet that just, explains how the tool works, what are the underlying, models and equations and formulas that sit there. There's some input sections as well. So, putting in your input road scenarios, and those are aligned with the input data available from the PMS. We've also got some, sample fleet and, electric vehicle uptake scenarios that you can select from, just to sort of illustrate that, if you have a high, uptake of EVs, how will that impact your carbon emissions? If you have a low uptake, how will that impact? So you can do a little bit of a sensitivity there. And then the sort of remaining sheets are, providing those calculations. And then there's obviously supporting data that goes into those calculations in the tool. And so this is just a little screenshot of part of the calculations sheet where you can, just see it's got similar information to what I just showed on the previous slide around this is how the fuel consumption is calculated. In terms of the workflow of the tool, so this also sits in that in one of the workflow sheets there in the demonstration tool. And what it really does is just steps through how each of, how you can interact with the demonstration tool and, what happens at each step. So, it starts with the road scenarios saying, go to sheet 3A where you can input, you need to input the following data. So, length, speed limit, ADT breakdown by the Austroads 12 vehicle classes, and a forecasted IRI over a 30-year period. And then, you can then go in and select your input fleet and EV uptake. And then it just sort of steps through how the fleet forecast is performed. So that's the migration from ICE to EV. And then there's essentially the calculations that will show it just different levels of granularity. So this is just a little screenshot showing that input road section. So you can see there's 3 components here, which is inputting your your road section scenario. So you might want to test, for instance, the same road, and you might want to see what's the impact of a different speed limit. So you can then put in your ADT breakdown in the next section, and then there's obviously that forecasted road section roughness. And this is just showing a little bit around what that sort of output looks like. So you can see for each road section that or scenario that you evaluate and the row, you can see the annual greenhouse gas emissions for that road section. So that's combining at whatever sort of composition the fleet is in at that point in time. And then you can sort of see that over the lifetime at the end as well in that final column. And so next we're going to talk about the embodied emissions work. And so Rohit, I will hand over to you.
Thanks, Daniel. So I'll now go through the embodied emissions modeling component of this project. So embodied emissions refers to the emissions relating to the maintenance, preservation, rehabilitation, and renewal activities on existing road pavements. So essentially, we're looking at the emissions relating to road maintenance activities. So it is important to note that for the embodied emissions modeling, we're focused on the Scope 1 and Scope 3 greenhouse gas emissions, so which are the direct emissions produced by fuel combustion and the indirect emissions due to the upstream production of the fuel source. Next slide, please. So in terms of the overall methodology, we first compiled a list of TMR's current library of pavement treatments, which are classified as either surfacing treatments, rehabilitation treatments, or capital works. We then map these treatments to the equivalent processes within the SAT4P tool. So these SAT4P processes provide the emissions factors for the pavement materials and the construction activities that we used on this project. For the emission sources that are included in the modeling, we have the emissions from the material production, the fuel use from the construction activity, which is the diesel consumption of the plant and equipment on site, and also the transport of materials to the site, including empty vehicle return trips. Next slide, please. So this slide just shows a summary of the TMR pavement treatment list used on this project. And as you can see, we have 5 capital works treatments, 15 surfacing treatments, and 12 rehabilitation treatments. Next slide, please. So similar to the enabled emissions tool, we have developed a spreadsheet-based embodied emissions tool, which can assign emissions to each maintenance treatment, aggregate emissions across multiple treatments over the pavement lifecycle, and also allow the user to scale the results from an individual road segment to network level results. So the figure on the right here just shows the contents page of the embodied emissions tool. So we first have a workflow sheet that provides an overview of the tool and includes further details on each of the inputs within the different sheets. We also have the main calculation sheet, which is where the calculations are performed to calculate the embodied emissions from TMR maintenance treatments based on the user-defined inputs. So we then have two supporting sheets, which contains the associated data on the emissions factors, the different linkages to the SAT4P processes, and the data on vehicles, products, and materials that are used within the main calculation sheet. Next slide, please. This slide shows a snapshot of the main sheet within the tool, which is where the user can input the details of the maintenance treatments, including the treatment dimensions and the haulage information, such as the approximate haul distance and the haulage vehicle. So following this, the relevant calculations and searches are performed to calculate the emissions outputs in terms of the product emissions, transport emissions, and treatment emissions, as well as the total embodied emissions. So all emissions are calculated in tons of CO2 equivalent. And for ease of access, all treatment-related inputs are all drop-down lists, with the exception of the treatment year and the treatment dimensions. Next slide, please. So this slide just shows a case study demonstrating how the embodied emissions tool can be used. What we see here is the impact of haul distance on the embodied emissions associated with a typical maintenance schedule over a 30-year life cycle for a dense graded asphalt pavement. We can see that the majority of the total emissions are associated with the products, that is the embodied emissions of the input materials. The treatment-related emissions, which is the diesel usage of the on-site equipment, is relatively minor at around 2 to 3%. We can also see that the transport-related emissions have a very minor impact for short haul distances, but as the haul distance increases, it can almost be the same as the treatment emissions, but it is still relatively minor compared to the product emissions. So what this case study basically highlights is the significant contribution of the product-related emissions to the overall embodied carbon of maintenance treatment activities. I'll now pass back to Daniel, who'll go through a trial application of the two emissions tools.
Great, thanks, Rohit. So I will talk a little bit about some application of these, these frameworks and approaches, and show a little bit of how this can look over a bit of a life cycle analysis. So for this, we did some work, and this, as we mentioned before, this also supported a parallel NACOE project, A68, which was looking into, the sort of whole the broad impacts around the transition to low and emission vehicles, particularly heavy vehicles. So we worked alongside on this, and so what we looked at was a representative road network. So it was a coverage of various representative sections across Queensland of different road types and categories and compositions. And so work was done to essentially look at different types of that, how that would change over time under different conversion or migrations from, combustion engine vehicles to low and zero emission vehicles. Under that sort of that forecasting of the different, different migration scenarios, we did some modeling work to look at the different, traffic pavement condition and, various treatment strategies over time. And that was done for a number of different road agency budget constraints. So you sort of, if we start at the bottom, that's sort of a, an ideal optimization where there's no constraint in the road agency budget. It's what do you need to do to achieve, the ideal or optimal levels of service and, pavement condition over that time. And then progressively, reducing that budget so that our modeling work can look at, under different constrained scenarios, different decisions need to be made in terms of, maintaining the network. And then obviously there's impacts that flow on into, not just the, pavement condition, but also into the emissions. And so that's where we, use this data to essentially assess the life cycle greenhouse gas emissions from the vehicles using the road, so that enabled emissions, and also from the maintenance, the maintenance treatments that were applied over that 25-year period. So, with this is again sort of showing a number of different, breakdowns of the different types of roads that were looked at in this analysis. So it covered, the sort of, your large, intercity regional line haul roads, things like interregionals, major through roads, and also, distributor and connector roads. And we also looked at some more urban roads, particularly some of the arterial and interregional roads. Again, the road agency budget scenarios that we examined, and then we looked at a few different uptake scenarios of low and zero emission vehicles, essentially EVs. So the three sort of cases of that migration were the base case, which assumes that there's no migration away from combustion engine vehicles. Then we looked at sort of a medium and a very high. So what that essentially looked at is a sort of linear increase that at the end of the analysis period, you had either 66% in the medium case or 100% in the very high case of vehicles that have migrated over. So it's that sort of a bit of a stage transition. It's not a what does it look like if everything switched tomorrow. Alongside that, we made some assumptions, which was that if you think of the smaller passenger vehicles, they would transition independent of the analysis period. And we also applied a constant traffic growth rate per year. So if we start to look at some of the results here, I just wanted to show one example just to give you a bit of an illustration of how that migration from ICE to LZE would happen over time. And so this is just showing in the vertical axis, you've got the annual traffic for a section. And then you've got in the dashed light green line is the sort of total traffic. And then you've got a dark blue and a sort of lighter blue, we can see which are ICEVs and LZEVs as well. So if you look at the sort of the bottom one that starts at 2023, that's the low and zero emission vehicles. And you can see that over time, that progressively, increases in the proportion of the traffic until you get to the end of the analysis period, and it's now at 100% of that total traffic. So you can see that conversion shown here. So if we just look at, we can do a bit of a comparison and just see what does that look like under the different scenarios that we were investigating. So you can see under the base scenario, the ICV is equivalent to the dash total line. So there's no migration towards low and zero emission vehicles. If we look at the medium, you can see there is some conversion. So that's whereby when it gets to the end, it's around 66% of the total traffic has converted. And then similar to what I showed before, there's that very high uptake where by the end of the analysis period, it's completely migrated to low and zero emission vehicles. So what does that impact in terms of the enabled emissions? So if we look here, we've got a number of, I'll show a series of charts. In the vertical axis, there is the annual greenhouse gas emissions. So this is the annual emissions from the vehicles traveling on the road. We've got the three colors on the chart represent the base uptake case, the light blue is the medium uptake case, and then that green is the very high uptake case. And so this chart is shown for one of the constrained road agency budgets. So this is 10%. And what you can see quite clearly is that as you increase your proportion of vehicles to LZE, you get a, relatively significant reduction in annual greenhouse gas emissions. And so, as you would expect for the very high case, by the time you've done a complete migration, you can get pretty much near zero greenhouse gas emissions. So I should add as well that in the sort of supporting data in the demonstration tool for the enabled emissions, there's a forecast of the electricity grid carbon intensity, and so that feeds into the low and zero emission vehicles shown here. So as the grid progressively transitions to more wind and solar or other types of renewable generation, the grid has a lower carbon intensity, and that's reflected as you increase your migration towards those vehicles. If we look at sort of the 50% road agency budget, again, we can see a similar impact. There's not a huge difference between the 10% and the 50% road agency budget in terms of the total carbon emissions, and I'll show those in a bit more detail later on. But you can see the broader trend, and one of the most significant sensitive impacts here is that migration of the vehicles away from internal combustion vehicles. And then just showing again, you can see a similar trend as well for the unlimited, unconstrained road agency budget. So what does that look like in terms of our total? So if you go over that 25-year analysis period, we aggregate them all up. What we've got is in the vertical, we've got each bar showing the life cycle greenhouse gas emissions, and for the different road agency budget scenarios, so from 10 up to the unlimited unconstrained scenario, and for the different low and zero emission vehicle uptake scenarios. And so what we can see is there's some minor impacts and changes across the sort of road agency budget. But the sort of significant changes are observed when the traffic has been migrating away from those combustion vehicles. And so I just wanted to show this chart as well, because it sort of links, we looked at, there's not a huge change across the different road agency budgets. And so we looked into this a little bit. And so what I've got here is just showing one of the examples of the totals again for one of the uptake scenarios. I think it was the base. And so in the tool, we obviously incorporate roughness. So as you sort of move to a less constrained budget, you end up with roads that are smoother, and therefore you end up with roads that have less, they'll require less fuel to traverse them, and therefore there's a slight reduction in fuel and emissions as well, in carbon emissions. And so as part of this modelling, we did some work looking at, well, if you are under these different budgetary constraints, and the roads will get rougher in certain places. You see more deterioration across this. At a certain point, when that deterioration crosses a certain roughness threshold, we implemented some speed restrictions. So you can imagine it, if you're going over a road and it's a bit rough, you have to either be recommended, or you'll feel necessary to have to travel at a slower speed. And so what we can see is under the sort of the 10, 25 and 50% constrained scenarios, we saw more and more instances where vehicles had to, or the road sections, we would have to apply a speed restriction because it would cross that roughness threshold. And so you get a little bit of there's that trade-off. So you end up seeing, well, we had to travel slower, but there's a longer period of travel over there. And so you end up with a bigger proportion compensating for that, but not necessarily offering you any, carbon savings from an enabled emissions perspective. So now just moving to the embodied emissions. So the treatment emissions over this 25-year analysis period. I will just show, we did again just the greenhouse gas emissions each year, and I've shown a few different road agency budgets. So you've got 10% in the top row, 50% in the middle, and then the sort of unlimited, unconstrained scenario. And so as you would sort of expect, as you have a greater budget, you have less budgetary constraints, you can perform more maintenance, which means there are more carbon emissions associated with those maintenance treatments. And I think one of the interesting things to note here is in the unconstrained, unlimited scenario, there's a large spike at the start, and that's part of that modeling optimization where it does it prioritizes to do a number of treatments early on, so that it can, because there's no budgetary constraints for it. And if we just look at those total, the total life cycle carbon emissions from the maintenance treatments, we can see a sort of, a similar pattern. Interestingly as well, if you look at the sort of road agency budget, that's quite sensitive, as you move from 10%, 25, 50, 100 up to the unconstrained, you can see quite a significant difference. But you can also see a bit of a difference across the uptake scenario as well. And so the uptake scenario, also reflects some impacts of increased loading on the network as well. So then, might have to have a bit more treatment depending on what your loading conditions are on the network. But I will point out the sort of scale of this. And if we, look to aggregate them all up together, where we've sort of got the enabled in the blue, and then stacked on top are the embodied from the maintenance treatments. What we can see again is, the similar picture where the user carbon, forms the vast majority of the emissions. But you can see a noticeable difference from, a noticeable contribution from the embodied carbon, particularly as you move to the sort of less constrained scenarios. So just a quick sort of a bit of a summary of what we've done in this project. So we've obviously developed, some frameworks and demonstration spreadsheet tools to estimate the carbon emissions from, the enabled perspective, so your user carbon, and also embodied emissions of maintenance treatments. So we just presented around some of this trial application, looking at a representative network for different scenarios and budgetary constraints. And a lot of this work as well fed into, one of the NACOE parallel projects that was, specifically looking at the impact assessment of the introduction of low emission heavy vehicles. So I guess just the sort of key findings, if we can draw out just a few sort of, real key points on this. If we're thinking, and, we're looking at the maintenance carbon emissions, the budget is really the dominant driver. And that's I think is to be expected, because if you have a higher budget, you can do more maintenance. Therefore, there's going to be more emissions associated with more activities. We see the lower budget scenarios obviously show lower embodied emissions, but that implies that there's greater deterioration of the assets. In terms of, what dominates, again, the life cycle carbon emissions are dominated by the enabled, your road user emissions. And under the low to moderate budgets and relatively low or no uptake of low and zero emission vehicles, the embodied emissions are anywhere from around 1 to 5% of that total. As you start to relax those budgetary constraints and increase the uptake of low and zero emission vehicles, the embodied emissions can reach up to 15% in some cases. So, what we saw in terms of the effect of uptake of low and zero emission vehicles, obviously a higher low and zero emission vehicle uptake reduces the enabled emissions, but we didn't observe it materially reducing the embodied emissions. And I think as the enabled emissions fall, so if we look at this on an annual basis, there was the trend of the enabled emissions reducing. What we would then start to see is maintenance-related embodied carbon becomes a more prominent feature, and would be something to, it would take up a larger proportion. Over the total life cycle, it might be 25%, but when you get to sort of the last few years, it might be, somewhere upwards of 90 or 100%, depending on the proportion of low and zero emission vehicles on the network. So I think that's really the key takeaway that we wanted to communicate from this work, is that while it's probably not a significant impact right now, the maintenance emissions as a proportion of the total whole of life, as this transition away from combustion engine vehicles happens, maintenance emissions and other sort of emissions will play an increasingly large role. And so they'll need to be, I think, accounted for and certainly considered. And so just in terms of some of the future work that, we've sort of identified, I think there's, a bit more work that could be done to sort of look at some of, some of these parameters in a bit more detail. I think there's a few interesting elements around speed limits, treatment times and changing them that could be interesting to see their impact on the enabled and embodied carbon emissions. And we did a bit of work in the parallel project looking at the sort of broader road user costs, so your vehicle operating costs and other total transport costs. And I think something that's underrepresented and not covered right now is that sort of the vehicle operating costs associated with low and zero emission vehicles. So I think that's certainly something that should be looked at in the future. And I think in terms of where we will, where this research, can be used, I think, Andrew, I'll hand over to you to sort of discuss the implementation aspect at TMR.
Thanks, Daniel. So certainly from a TMR perspective and looking at our network lifecycle modelling, our new advice tool, so asset deterioration valuation investment calculation engine, will be the main tool that will implement this capability in for both embodied and enabled emissions for our maintenance preservation activities. Advice already has the ability to calculate embodied emissions in terms of we've provisioned within the structure of the solution that capability, but we still need to do some work to implement that. So we will use the A67 tool as well as SAT4P to generate some embodied emission rates for each of our maintenance treatments. So they'll be defined for each of our road stereotypes and for each district. For enabled emissions, that's really dependent on, first of all, the implementation of the ATAP vehicle operating cost model, which we're planning to incorporate in release 1.2 which at this point in time is expected in January 2027. And subsequent to that, we'll be able to implement the costing for enabled emissions. That will be in a subsequent release, and that's likely to be early 2028, but it still needs to be prioritised as part of the implementation. I'll also say that we will make those models available, so there'll be some ability to run analysis at a district level, just understanding the enabled and embodied emissions through those tools. Yeah, that's the brief overview for the implementation side. I'll hand back now to Rosie to help run us through Q&A. Thanks, Rosie.
Thanks, Andrew, and thanks so much to our presenters today for the insightful webinar. We do have quite a few questions, so just a reminder to pop them in the Q&A if you would like them answered. So the first question is from Duncan. So off topic, you mentioned a NACOE project assessing impacts of low emission vehicles. Is there a similar impact assessment project planned for the CML to GML transition that is planned in updates to the HVNL?
Yeah, I was going to say Andrew or Ty, do you want to field that one?
So I'll jump in from a TMR side. So we don't have a plan to undertake some specific modelling for CML to GML. We have provided feedback based on the A68, which was looking at low and zero emission vehicles, which included a mass increase as part of that assessment. But at this point in time, we don't have a study planned looking at the impact of the CML to GML change. Ty can probably fill in his knowledge of what's occurred at a national level there.
Thank you, Andrew, and thank you also, Daniel, and everyone for the presentation and the attendees. At a national level, we've not had exposure to the actual detailed studies that's been undertaken. But what has been done, an example is in Victoria, a comparison was made between CML and GML in a whole of life case, very similar to what we've been doing in that, using total transport costs, road user costs, etc., with all the factors that involves. And there's also been some trial calculations lately with several other studies. Now, in terms of the sweet spot of investment, if investment does move to a more fit for purpose, optimal spend, then the CML, the opportunity of productivity benefits to CML is being shown as a benefit overall at a social, economic cost level. But the impact coming with that is actually a demand for increased road agency costs. And it's on that side where I just make the point that we continue to face a challenge. We can reduce trips through more high productivity vehicles, which is really the result of CML. But to actually hit the sweet spot and deliver it to the community, there is an investment implication. If that investment doesn't turn up, then impacts on vehicle operating costs can go in the other way. It might not reduce. So that's the simple answer. What I was going to do was offer a few comments in a response post the webinar, because there has been some other work that we've been doing lately in NTRO to put a feel for a number around this. Thank you.
Thanks, Andrew and Tyrone, for that one. Our next question is from Louise. A very interesting project and worthwhile modelling. There seems a lot of overlap between the modelling you have undertaken and the modelling capability of the SAT4P application that was developed by NACOE and Warrap. Keen to understand if these two projects are collaborating and sharing data and information.
Yes, yeah, definitely. So I think there's similar approaches, but certainly in both approaches to the modelling. And as Rohit sort of went through as well, part of this work was to, one was to review what was in SAT4P, and be able to use some of that information and data sets out of that. And so, part of what we've found in this is also feeding back into SAT4P into where, where there's some gaps in coverage that need to be expanded. So yeah, certainly working in both sides very closely with that.
Thank you, Daniel. Our next question is from Lynette. For enabled emissions modelling, good to see that pavement roughness is accounted for. Was applying typical drive cycles, speed/time traces considered to better estimate fuel consumption?
Yeah, this is a very good question. Thanks, Lynette. It's one of those factors of when you're modeling vehicle fuel or energy consumption, there's sort of various trade-offs that you can make. So if you go down to a sort of, you're looking at a drive cycle, which essentially will give you information on, vehicle speed versus time. So you can see when a vehicle's going on the motorway, it would speed up and it would sort of stay ideally at, motorway speeds. And when it's, in urban areas, there's obviously lots of variation in that speed. Doing those sorts of individual vehicle level models is, it's rather difficult to scale that up. And so as part of this, where we wanted it to sort of be scalable up to a, to a network level, you don't have access to, I think, sufficient duty cycles to cover that full, full network, but then also the computational burden becomes too much. And so that's where we've sort of built on the ATAP approach, which has got a lot of work looking at the sort of instantaneous speed effects, but just it's sort of a higher level assessment there.
Maybe
Thanks,
if I
Daniel.
add something, Daniel,
Please.
For Lynette, is there's work which is now at a very advanced state, bringing speed acceleration cycles and volume capacity ratio effects into the ATAP models. There's been attempts at that before, but that will now be part of the ATAP models so that we're dealing with time of day and other things in traffic interaction, and that'll give a much, let's say, more refined, better estimate of what the impacts are, both in fuel consumption, etc., but it's through its output into carbon. And that work is getting close to finalisation under PV2 and will be available for wider application.
Thanks, Daniel and Tyrone, for that one. So we've got a couple that have come through from Jen. So the first one is, why don't enabled emissions go down under a less constrained budget? I would have expected more frequent maintenance to result in less deterioration, smoother roads, and hence reduced vehicle emissions.
Yeah. So this is something that is an interesting one, where what we had observed in terms of the enabled emissions is, you do get smoother roads or, better maintained roads. And so you get a sort of small reduction in, fuel consumption and therefore emissions. When you go under the, the lower or you say like the more constrained budgets, for instance, so, you get a road that deteriorates more, so you get a roughness level that would be higher. And so where you start to, and you'd think, okay, we're going to have a higher roughness road, therefore there's going to be more carbon emissions. When it deteriorates to that point where you actually need to implement a speed limit reduction, that's where you start to not, it sort of starts to level that off and you start to see not that significant of an impact across that. So if it was traveling, if all things were considered equal, where you didn't have a speed limit reduction, then certainly that would be the trend that we would observe. But if you have that approach of you need to drop the speed limit because it's a little bit too rough to travel on, then that offsets the emissions reduction that you would get.
Thanks for that, Daniel. So the next one, are MRWA planning to include carbon budget as one of the constraints or factor that is considered in developing an optimized asset management program? And or will they consider carbon impact as one of the factors in their optimization method?
I assume it's meant to be TMR, not MRWA.
I assume so.
So I can answer that from a TMR perspective then. So certainly when we're incorporating this within our advice tool, there is the ability for us to include carbon emissions as a cost or benefit, be it embodied or enabled carbon. So it will be available to us within our optimization capability. Now, exactly how we would implement that, initially it will be a factor that will help inform understanding of the benefits of different network maintenance strategies. And time will tell, I guess, in terms of whether we are actually optimizing the network based on carbon or total transport costs, including carbon. Thank you.
Thanks, Andrew. So our next question, great presentation, thank you. How is improved productivity from better quality road network included in the overall assessment of the value of maintenance works?
I think, I guess from that perspective, some of the work that we did that has fed into the other project has been looking at that total transport cost approach, where it's looking at the broader societal costs and benefits as well. So I think that's all that sort of takes into account things like we talked about road user costs like vehicle operating costs. We also considered the impact of crash costs or reducing crash costs by having a better maintained road network as well. So it was all of those factors, I think, that fit in that I hope sort of form that broader productivity piece.
Cool. Thanks, Daniel. So we've got 3 more questions. I'm aware we're a little bit over time. So Lynette is saying, might reduced road agency budget increase risk of major maintenance requirements and additional embodied carbon? Preventative maintenance can extend service life.
Yes, I would say certainly that is the case. I'm not sure if Tyrone is still there. Might be having some internet problems, but yeah, certainly it's a big thing that Tyrone would certainly talk about is the sort of stitch in time approach. And so it's if you continue to defer maintenance, then certainly I think at some point there comes a time when you need to spend a significant amount of money to perform major works. And there's some of the things that we've seen in our general modeling work here, that if you can sort of level out those costs, it on the whole your life cycle analysis comes out to be lower.
Thanks for that, Daniel. So we've got a couple more. Is there any thought around lithium battery disposal with the increase of zero emission heavy vehicles?
Yeah, I mean, there's lots of work going into that, from a number of perspectives. If you think of a zero emission heavy vehicle, probably the largest component of cost when you purchase one is from the battery. And then there's also obviously the embodied carbon to make the vehicle. There's the battery is also that largest component of that embodied carbon, to make the vehicle. So, there's a lot of work that's happening, in Australia, certainly there's a lot of work looking at future recycling of batteries. So I know there's a number of different CRCs and initiatives looking at how we can deal with that, because it's not just going to be a vehicle problem. There's also, an increasing number of large batteries being used as, energy storage for, domestic and commercial applications. So I think it's still, early days, but, there's lots of people looking to solve those problems.
Thank you, Daniel. And our last question for today from Pratap, is that roughness factor coming from consideration of ease of riding / condition of the road? Would the model consider road gradient as well? So that might be in relation to previous question.
Yep. So the roughness is specifically, obviously the surface roughness, but then in these models, and they're sort of, they're freely available online. If you look for ATAP PV2, you can find the documentation and guidance there. What it does include is in those K1 to K5 model coefficients, they are also dependent on things like elevation and, I think, curvedness of the road. If you have a particularly windy road, there's also those coefficients will change depending on that road condition beyond the sort of roughness itself.
Great, thank you, Daniel. That's all the questions for our Q&A for today. So thank you everyone for attending today's session, and thank you again to our presenters for today's webinar. If you did have any other questions that you wanted to ask, or if you wanted to get in touch with our presenters, feel free to email the NACOE email address that you see on the screen, info@nacoe.com.au. Today's session has been recorded, so you will be able to find the recording on the NACOE YouTube channel and the NACOE website later on today. Thank you everyone again for attending, and we'll see you at the next webinar.